Okay, so this is the acoustic meter, and we have also other device. This is the tuning device. When I turn it on, you can hear, this is the basic tone. And the basic tone is with the loudness of 113 decibels.
Here we can see the exact parameter.
And this is the tuning device, so we have to tune every time we use the acoustic meter before usage and after the usage, just to check if all the levels are leveled. We have already switched on the acoustic meter, so we can see that it basically all the time measures the loudness. But now it's only on, so it doesn't fulfill the writing of that measurement. So we cannot. So if we try to download the data from the acoustic meter, we will not be able to see anything. We have to turn on the measurement before preparing the data. Okay, so here we have several options. And to enter the menu, we have to use Shift button. Yes, and we have the functions. Can you see it? Yeah. Okay. And we have the functions, and we enter the functions, and we use calibration. Okay. This is simple. It's just the arrows. So we will try to calibrate the acoustic meter, and what we will turn on is auto calibration, just to make everything easy. This is the element that protects the microphone, because the microphone is rather delicate. So we put the acoustic calibrator tuning device on the acoustic meter, and we already hear that it's switched on, because it's switched on automatically as it's on the device. And then we just start with this button, the calibration. And here we can see the level as it levels to 113 decibels. Sometimes there is a small ending because I'm talking, so I'm a little bit disturbing the device. But once the level is settled, we can say that the device is calibrated, and we just stop with the start-stop button. We also have to switch off this. And we can do the measurements. So this is the microphone here. And we put a little bit of foam. It's basically to catch if there's, sometimes when you go outside, we have the wind, so just to even the acoustic field around the device. And so now we will do the analysis of loudness of us talking here in this room. Okay? Okay. We are in the scenario of not such a large room, so the acoustical reverberance is present. Probably you can hear a little bit of decay after my voice starts.
Yeah, kind of.
But it's not very long, right? Okay. So let's call it a typical acoustical environment. We have a little bit of soft floors. We have reflecting walls.
Furniture.
Yeah, we do. We have furniture. Some of them are absorbing. So it's more or less like would be in the house, maybe in a little bit larger room.
Yeah.
So let's see how loud is our conversation. Now we will do the measurements of the levels. Okay. So we can say loudness. It's not such a perfect, precise notion, but for subjective perspective for a human being, loudness is a good thing to imagine what we will be measuring now. Okay. So I have to go back to the menu, and I will select the measurements, and I will select, I have to turn it around. I think I went to the function. Yes, measurement function, and we will use this function, so it's the meter of the level. of the acoustical pressure. So as we are not talking, we can see that the average acoustic level is around around 40 decibels. It's still quite loud, but we hear the cars passing by and so on. Okay, so now let's measure our conversation. Why are you interested in acoustical architecture?
Okay, so as I said, I watched your presentation and it was really interesting. I was kind of shocked by the fact that we ignore those European rules, let's say, and actually no one cares. Yeah, and the score, can I call it like that, the score?
Yeah, definitely.
So the numbers in the city center nearby, like our school and the place I live, were so huge, and I was just shocked. So it's simply interesting to me due to this fact and due to the fact that we ignore those rules.
Yeah, that's true, and we'll go outside also. We will see what happens by Wyszyńskiego Street today.
Yeah.
I think it was quite loud when I was coming here. So, our conversation is about, it comes up, well, it's about 50-60 decibels, so we are not that loud for the conversation. But if you would suppose to be in 60 decibels all day long, that would be a lot. So when the children are learning in school and the teacher is talking, they are talking, so for 8 hours they usually are exposed to even more than 60 decibels. Yeah. So that's quite a lot. As you remember from my presentation, from 55 decibels we start to feel annoyed and stressed, right? So these are not such a good levels. Okay.
After downloading data to the computer, we can see the graphs that we've seen on the meter just as a set of colors. The line that interests us the most is the green one because it expresses the sound level that was measured according to the correction curve A. The correction curve A and sound levels I will be discussing with you further on the classes. So this is the time when we haven't been talking, and you can definitely see the part when we've started the conversation. And as we go to the log data and we see the exact measurements, we can see that time when we haven't been talking is about 30 decibels. It even comes up to 26 decibels, which is quite good for environment when we are inside and there is no additional activities inside. Once we've started to talk, we've exceeded 70 decibels and we even achieved the level of 78.8 decibels. So as you can see, the conversation is already a quite loud phenomenon inside of the space of the room.
Okay, so now we will measure the reverberation time of this room. So we know the decay time. After we stop talking, this level is dropping down by 60 decibels. After 60 decibels, we stop hearing it. We'll use this balloon and use this pin that we use for our project to measure the reverberation time. The measurement is basically based on the impact sound, so there has to be strong impact sound that triggers the measurement device, and then it calculates all the reflections that are coming back to the measuring device. Of course, we shouldn't be in the room. Usually you just leave because we are also absorbing material, but of course we will be here. And you have to protect your ears. I will tell you when. I'm just gonna check, I'm just gonna start. Yes. So now it waits for the trigger. My speech is not loud enough. Okay, cover your ears.
Okay.
It's calculating. And here you can see the ambient of the reverberation time after the sound ceased. We can also see that there is a strong response late in the room, so there is some sort of echo. And I think that it's because we have open doors to the corridor and some sounds came back from the corridor. So we're supposed to close the doors. And we can see that the response is not immediate, so we have very strong reflections that are a little bit late towards the first sound, which, if the room would be larger, would probably make us hear a disturbance of sound. But the room is not that large, so this doesn't have such an impact to our hearing. And the reverberation time, this is reverberation time 30, so it's 98, so it's almost 1 second. So this room response is about, we have to calculate by 2, so it's about second and 8.
Okay.
Yeah, 1.8 seconds. So it's quite a lot, because it kind of reminds of a concert hall, actually, here in this room. So that's quite a large reverberation time. And it's probably because we have quite large room and we don't have so much absorbing materials here.
Yeah.
Okay.
Windows in front of us.
Yes, definitely. Okay, so that's our measurements for today in this room.
This is the graph of reverberation time in the room, and we can see here a very quick decay at first, and then we can hear this response that we had from the corridor. So you can see it exactly here on the graph. And in order to see what we have seen on the acoustic meter, we can have a look at octave graph, and here we see the frequencies, and here we have the acoustical pressure, and you can see the response of the room depending on the frequency here. And if we want to see the information about the time that we've measured, we can see it here. So here you can see our measurements. And of course, this is for reverberation time 20. So if you want to get the full reverberation time, you have to multiply that numbers by 3. These are for every frequency, every basic frequency that the measuring device is calculating.
Okay, so we are now in the space of huge reverberation time. So tell me, what are you going to cook for dinner today?
Okay, so today I'm planning to cook lasagna, and it's going to be vegan lasagna.
Wow!
Vegetarian to be precise. Yeah.
Okay, does it contain spinach?
No, it's not. There will be tofu. Yeah, tomatoes, obviously, some pasta, some sauce, with butter and with milk.
Wow,
But no meat.
sounds great. I like this kind of things without meat because they are more creative.
Yeah.
Right?
Yeah, they are, and you're not that, I don't know, maybe not full, but yeah, I guess you can feel better.
Yeah, that's
Later.
true. Yeah,
It's not so sleepy.
Yeah, it's not so sleepy. Although the cream and butter
Yeah.
might get you to sleep.
That's true.
Okay, so as you heard, we are in the space of long reverberation time. It decays slowly. And now we will do the experiment with the balloon again. So the meter is waiting for trigger. Cover your ears, please. It still continues.
Yeah.
see the calculations. Okay. It's the half time, so the 30 seconds, the RT30, sorry, it is 3.88 seconds. So the reverberation time is almost 8 seconds in this space. It's like a Roman church, almost. And we can also see the response from the room. Here you can see, after trigger, that we have a lot of reflections coming back late. And then we have a very strong echo. I hope you heard it. But this is exactly, on this graph we can see exactly the echo here.
So this is the graph showing the time of decay from the balloon that is in the hallway. And you can see that the acoustical pressure drops down by the 60 decibels. Here you can see an echo. These are the most common frequencies that are being used for acoustical measurements and acoustical calculations. Also, we can switch into the octave graph, and we can see the graph that we have seen on the acoustic meter. So you can see depending on the frequency, the acoustical pressure. So there is a huge response in the higher frequencies that we have seen also on the acoustical meter. And the time that we've measured is visible here. And here you can see the length of the reverberation time depending on the frequency. And you can see what we have measured. This is for reverberation time 20, so we have to multiply that by 3 to get the final results. We are now outside. As you can see, as you can hear, there is no reverberation time. So tell me, what's your favorite time of the year?
Okay, so, well, today we have such a beautiful day, and spring is coming, so I can say it will be spring, and all the trees and flowers that are blooming, yeah.
Okay, great. I think my favorite time of the year is also spring. We can also see the flowers that are already appearing here. Okay, so as you can hear, there is no reverberation time, and so we will not do the experiment with the balloon here, because basically the sound that we are producing is traveling everywhere up to the sky, and it kind of dies out because of the friction of the ground and of the air and all these things that are around us. We don't have the sound coming back to us. A little bit of sound is coming back from the bench, for example, but it will not be captured by the meter.
How about other noises? Can we check that? If we have such noise?
Yes, we definitely can check that. I think we have already the meter turned on, so we will be able to show you on a graph our conversation. I'm very close to the meter now, but I will just go ahead. And now, if we stop talking, we will be able to record what is going on outside. So we have the traffic and we have the traffic light. So the traffic kind of stops at some point and comes back. And now we will wait for one traffic cycle to record everything and to measure everything with the meter. Okay? Okay, there will be never a full silence here, because once the one traffic is
stopped the second appears, but probably we can see the cycles. You can see the cycles on the meter. Now it came to 75 decibels, which is still loud even in the Polish regulations. And we can see the cycles of the traffic as well. So that's a good measurement. Okay.
Maybe we should add that it's like 2 p.m. so it's not even that many. There's not that many of cars.
In the summer it will be a little bit better because there will be more trees, more foliage, which doesn't stop a lot, but it stops some of the noise of the year. Of course, if we would move closer to the university and more into the park, this loudness wouldn't be such huge thing, such huge problem. But still, we have benches here for resting. So some people will use that, especially in the summer. So yes, so these are our measurements. As you remember, inside we had maximum 40 decibels. Here it came to 85. But as we check the actual graph, we will see what the actual readings were, because this is some sort of average. Thank you. On this graph, we can see the outside traffic, and here we see the areas where it was a little bit quieter on our recording, and here we see the maximums of traffic. We can see the waves of the cars coming up and down. If we look at the table, we can see that the top data that we have experienced during our measurements and we have measured, we will focus on the level according to the curve A. And here we see that it was about 85.5 of decibels. So these are the top measurements, and the lowest measurements that we have registered were about 58.6. So both of these numbers are rather loud, especially that we have been in the recreation park.